In this video, we present our paper Quantifying Task Priority for Multitask Optimization, which has been accepted for CVPR 2024. We will dive into the innovative method we developed for determining task priority within the realm of multitask optimization. Multitask learning is a paradigm where multiple tasks are trained simultaneously using a shared model. This approach includes more efficient architecture design and improved optimization strategy for multiple tasks. In this work, our focus will be on multitask optimization. Each task in multitask learning has its own objective function, and these functions can sometimes conflict, leading to a decrease in overall performance. Specifically, improving the performance of one task might cause a decline in another, a phenomenon known as negative transfer. The main goal in multitask learning is to minimize the negative transfer and enhance the overall performance of a task. The primary goal of multitask learning is to find an optimal parameter theta star that minimizes the loss for our task. One of the main challenges we face in the optimization process is negative transfer. Negative transfer occurs when there are no parameters that minimize the loss for our task simultaneously, making it difficult to identify the optimal parameters. This difficulty arises because multitask learning involves multiple objectives, leading to inherent trade-off in task performance. To tackle this, we can approach the multitask learning problem as a multi-objective optimization problem. This allows us to redefine our goal as finding Pareto optimal solutions. Pareto optimality refers to a state where improving one aspect of performance cannot be achieved without sacrificing another. By aiming for Pareto optimal solution, we can better navigate the trade-offs and enhance overall performance in multitask learning. Earlier approaches in multitask optimization have focused on aligning task-specific gradients direction to find shared parameters. These methods offer theoretical analysis that demonstrate the convergence of optimization towards Pareto stationary points. However, these analyses face some constraints as they demonstrate that optimization converges to Pareto stationary points, which does not necessarily mean Pareto optimal points, as Pareto stationary points are necessary condition for Pareto optimality. So we introduced the concept of task priority to explain the limitation of previous work theoretically. Task priority is determined by measuring how task-specific gradient updates on shared parameters affect the overall multitask loss. Consider this inequality. If the update of task-specific gradient for task M on the shared parameter theta result in lower multitask loss compared to the update for task N, then we say that task M holds a priority over task N in theta. Our main theoretical analysis demonstrates that incorporating task priority in optimization process leads to better performance than when this information is not used. For detailed proof and further explanation, please refer to our paper. Building on our problem definition and motivation, we propose a new optimization method called connection strength-based optimization. This method is divided into two phases. In phase 1, we focus on teaching the network to capture task-specific details by running task priority. This helps the network understand which tasks are more critical at different stages of the training process. In phase 2, we determine the task priority within the shared parameters and adjust the gradient to preserve this priority. This ensures that the network maintains an optimal balance between tasks which it runs. By following this phase, our proposed method aims to enhance the overall performance of multitask learning. Imagine each input and output of the network's components as nodes. We can depict the computation flow by establishing connection between these nodes and then evaluate the strength of these connections to measure their interconnectedness. The concept of connection strength originally emerged in network compression, where connection in expensive CNNs were found. The idea is based on the intuition that larger parameters have a greater influence on the model's output. In our study, we reinterpret this intuition for multitask learning to determine task priority within the shared parameters of the network. In multitask learning, each task has its own distinct objective function, resulting in diverse connections formed during backpropagation. These connections are defined by the specific laws related with each task, which we term task-specific connection. The strength of these connections can be measured by the scale of the parameters similar to the conventional notion. Phase 1 of our method involves allowing the network to divide shared parameters into subsets based on task priority and update each task-specific connections sequentially. During this process, task priorities are learned by updating each task rows in turn. Recognizing task priority effectively enables the network to separate and handle task-specific information more efficiently. Task rows often fluctuate during training because of negative transfer, causing variation in overall multitask performance. To counter this, we introduced a secondary optimization phase designed to update gradients while preserving task priority. In phase 2, we utilize connection strengths. After determining the priority of task in each output channel, we align the gradient vector of each task with the gradient of the top priority task. By projecting gradient based on task priority, we then sum them and update the model accordingly. In the final step, we ran the two optimization stages. As training progresses, the probability of selecting phase 2 increases. This approach ensures that we preserve the task priority run in phase 1 while effectively updating gradient in phase 2. The reason for mixing these two phases rather than completely separating them is that the speed at which task priority is learned varies depending on the position within the network. This blended approach allows for more adaptive and effective optimization throughout the training process. For a detailed view of our optimization process, please refer to algorithm 1 in our paper. Previous studies have addressed conflicting gradients by adjusting them to align in the same direction. This method attempts to find an intermediate point among the gradient vectors, which often result in negative transfer due to the influence of the dominant task. In contrast, our approach enhances the network understanding of which shared parameter holds greater significance for each given task, thereby minimizing negative transfer more efficiently. The key distinction between earlier method and ours is the inclusion of task priority. By incorporating task priority, we can more effectively manage the interaction between tasks and ensure better overall performance in multitask learning. Here are our experimental results. The main results on NYD version 2 dataset are presented on table. Compared to previous method, our approach shows better performance on most tasks. It proves our method tends to induce less task interference. Similarly, our approach shows better performance on Pascal context dataset. We provide further experiment with various loss scaling method and backbone architectures in our paper. Our method successfully identifies Pareto optimal solutions for multiple tasks. In Figure 2, we illustrate the final task-specific loss and their average for NID version 2 and Pascal context dataset. Our approach exhibits the lowest average training loss overall. Furthermore, when examining each task individually, our method consistently demonstrates the lowest final loss across all tasks. This finding serves as evidence that our method expands the Pareto frontier beyond what previous approaches have achieved. Phase 1 of our method focuses on running task priority to discover Pareto optimal solutions. In our evaluation studies, detailed in Table 4, we investigate the impact of each optimization stage. When solely employing phase 2, we observe no significant difference in performance compared to previous optimization method. However, with the inclusion of phase 1, we achieved the lowest average multitask loss. Moreover, we present the correlation of loss trends in Figure 3. In this correlation analysis, values closer to 1 indicates that the loss of the task pair decreased together. During the initial stage of optimization, phase 1 demonstrates more effective alignment of loss compared to relying solely on phase 2. This underscores the importance of phase 1 in aiding the network to discern task-specific details, ultimately leading to the identification of optimal Pareto solutions. During phase 2 of our optimization process, the priority of tasks is likely to be maintained. We assess the top priority tasks within the shared space of the network and visualize the percentage of top priority tasks in Figure 4. This visualization illustrates the extent to which this task holds priority over the output channels in the shared convolution layer. We compare the scenario where only phase 1 is utilized and when both phase 1 and phase 2 are employed. Our findings indicate that phase 2, particularly in the latter half of the optimization process, effectively preserves the run task priority. This approach to priority allocation prevents any single task from exerting a dominant influence over the entire network, thereby promoting balanced multitask running. Combining both phases of our method yields superior performance compared to using each phase separately. As shown in Table 4, utilizing only phase 1 resulting in a lower multitask loss compared to a strategy that mixes both phases. However, integrating both phases ultimately enhances multitask performance. This improvement can be attributed to the normalized connection strength employed in phase 2, ensuring that no single task dominates the entire network. When the two phases are applied sequentially, performance declines relative to our mixing strategy. This decline seems to stem from the application of phase 1 in the later stage of the optimization. Continuously changing its established task priority disrupts the proper updating of gradients based on round priority, leading to performance degradation. Thus, our mixing strategy effectively balances the benefits of both phases, resulting in improved multitask running performance. In conclusion, this presentation provides a concise overview of our paper. For a more comprehensive understanding, including further explanation, theoretical analysis, and detailed method, we encourage you to refer to our paper. Thank you for your attention.